What's Gucci and the Coochie, everybody? Welcome to the show. It's your boy Vontae, aka Mr. Keep It 100, and we're about to go into a short introductory lesson over solutions. First, we need to answer the question of what are solutions. It's a pretty easy concept to remember. Solutions are just homogeneous mixtures of two or more compounds. So take, for example, the mixture between salt. Okay, don't laugh at the picture. I know it looks like dookie, but don't say anything. And water. When you mix these two things together, you get salt water. But in this case, the salt is evenly distributed throughout the entire collection of water. So in this case, our salt is our solute, or the thing that's being dissolved into solvent, or our water. So to remember these things, you can think as a solvent as like some really strong guy who like beats up people and like takes money from people. It's a strong thing, breaks things down. While the solute is like the weak, nerdy person gets picked on a lot, he gives in to the demands of the solvent. That's why you got this picture here of the weights and stuff and the nerd here. So easy thing to remember. Again, solute dissolves in the solvent. Always remember that. So next, we need to know how to better describe solutions. Solutions are either dilute or concentrated. Dilute meaning that there's relatively little solute in the entire solution, and a concentrated solution has a lot of solute, meaning it's stronger. And from this, we have 4 equations to better describe a solution composition more accurately. So the first equation is molarity. Molarity is going to be your best friend. You're going to use them a lot. That's why I got the picture of the sexy guy here. This is your best friend right here. Next, you have mass percent, the cool younger brother of molarity. Then you have mole fraction. Don't talk about him too much. He's like a nerd, a little complicated equation and whatnot. Then we have my least favorite, molality. It's like the creepy uncle who hangs out at the barbecues. You don't talk to him much. That's his equation. So these 4 equations all do the same thing, categorizing a solution. They explain the ratio of solute to solvent, or they explain the strength. So to give a better example of what a strength of a solution really means, I'm going to do a quick experiment. So sit back and relax. I'm going to show you one more time the equations. So molarity, moles of solute over liters of solvent. Mass percent, mass of solute divided by mass of solvent times 100. Mole fraction, there you go. And molality, moles of solute divided by kilograms of solvent. Okay, now for my little demonstration. What's good, everybody? I'm here in the backyard of my $40 million mansion, and I'm going to show you a little experiment to better illustrate the effects of molarity and how a solution changes when you add more solute to it. All right, everybody, so we're going to make a solution. In order to do that, I have 2 liters of pop and a stack of Mentos, which will represent our solute for tonight. And so essentially, 1 tablet of Mentos equals 1 mole of our solute. And if you follow the equation for molarity, the more solute that you have, the more concentrated your solution becomes. So let's say I have 2 pieces of Mentos, or 2 moles of our solute, and this 2 liters of pop. If I were to add this to this right now, our new solution will have a concentration of 1 molarity. If I add another 2 pieces of solute, the newfound concentration of our solution will be 2 molarity. So essentially, in this case, since our solvent has a volume of 2 liters, for every 2 pieces of solute we have, the concentration goes up by 1. So I'm about to show you what happens when we add all these Mentos to this pop, just for fun. All right, everybody, so I peeled back the cap of our little solvent container, and let's get it cracking, okay? Here we go. See, we got a lot here, so nice. All that. All right, so personally, that would have been a little bit better if it blew up. It was kind of underwhelming, but you get the point. So when you add more solute to a solvent and becomes stronger, becomes more concentrated, and its properties are intensified. So let's say if I were to add like 100 or 1,000 Mentos to our little pop here, well, I would have probably died. So there you go. Okay, so the next thing I want to go over is what happens when a solution forms. So I want to touch on the Cardinal Rule. And essentially this rule is pretty simple. It states that the same thing is supposed to be grouped together. And by that, I mean a polar solvent can only dissolve a polar or ionic solute, and a nonpolar solvent can only dissolve a nonpolar solute. It's very simple to understand. You know, you have to have two of the same things to make a reaction happen, essentially. So a solution forms in 3 steps. Initially, the solute breaks up slightly, so it goes from a big collective into smaller parts. Second, the solvent overcomes its own intermolecular forces. That's the things that holds the molecules together, the interactions between the molecules of what's dissolving the solute, to allow room for the solute to actually come in between it so that you can have a reaction. Third, you should probably know what that means, you know, to get together and you form something new. So with all this reaction, as you know, energy is used and transferred, and it can be described with this equation. Enthalpy of solution is equal to the enthalpy of the 3 steps that I touched over. So usually enthalpy of solution is a exothermic reaction, so heat escapes the system once everything's said and done, but there are exceptions as with everything. So to better explain this equation and how this will look like, to give you a better example, I'm going to do a quick demonstration. Okay, everybody, for this demonstration, I'm going to be using a balloon, which will act as our system, and myself. I am surroundings in this case. So let's think of the balloon as the system for the entire equation, right? And the system changes depending on what happens during each step during the formation of the solution. So let's say for step 1, the change in enthalpy is endothermic, so it's a positive. So energy enters the system. And let's say the second step is also endothermic, but slightly, so more energy enters the system. Let's say step 3 is extremely exothermic. Well, then the entire enthalpy of solution exothermic as well. So energy goes back to the system. Okay, so the last thing I want to talk about in this video is what affects solubility. And there are 2 main things on the surface level that does this: pressure and temperature relative to the system. Pressure usually affects gases, and temperature more so for aqueous solutions. First, we're going to talk about pressure and gases. So gas particles can dissolve in a solution, and at higher pressures, this effect is intensified. So say like I have some pop, and on top, above the pop, there's a little CO2 pocket and a little air in there. So below that, the concentration of gas particles in the liquid is higher than above it. And this relationship is shown through Henry's law, P equals Kc. P is the partial pressure of the gas solute above the solution. K is a particular constant given to you as a characteristic of the solution. And C is the concentration of the dissolved gas. So essentially, Henry's law reinforces the idea that a gas dissolved in a solution is directly proportional to the pressure of the gas above the solution. So meaning at higher pressures, more gas can dissolve in the solvent. Next, briefly, this is really easy with temperature. It's really simple. So for solids at higher temperature, the reaction goes faster. You know anything about kinetics, and thus dissolving occurs more rapidly. And typically, if you add heat to a solvent, it'll be able to absorb more solute. And that's just about it with these 2 things. So that's the end of this video. Okay, I have some guided notes that will help you solidify the information here. There's some practice problems, and thanks for watching. I'll catch you in the next one.